Alright, so welcome everyone to Dynamic Simulation and Control. This is Module 4, and under this process, now we are moving from the steady state to the dynamic state of Aspen HYSYS. And in this dynamic state, we're going to be looking at controls as well. We're going to be applying some controllers to the system, alright, to regulate different process variables. Alright, so what are we looking at here? What are the objectives? The objective is to understand and implement dynamic simulation techniques for time-dependent process behavior and to develop control strategies for process optimization. Alright, so the objective of this is to implement the dynamic simulation techniques. Alright, so we're going to be varying parameters or variables with time, and then to study the behavior of these control strategies which we're going to be applying for optimization. All right, so what are we going to cover in this? We're going to cover setting up dynamic model for transient process behavior. All right, so what is transient process behavior? Okay, so transient process behavior refers to how a process responds over time when it is transitioning from one steady state to another due to a change in conditions. All right, so it is the period of adjustment from one steady state to another is known as the transient behavior. All right, so we are going to be setting up that. We're going to be looking at some control strategy implementations. That's the PID, which the feed forward and then the cascade. Alright, so that PID stands for proportional integral derivative. Alright, so that's basically what it stands for, proportional integral derivative. And then we'll be looking at the feed forward and then the cascade control strategies as well. Then we're also going to be looking at the startup and shutdown simulations. Alright, so now let's go into it. What is dynamic simulation? Dynamic simulation is a modeling technique that represents how a system behaves over time, considering its state variables and how they change in response to various inputs and conditions. Alright, this dynamic simulation is a type of process simulation which models how a system behaves over time. Alright, so the dynamic simulation now, it's you're going to be varying your variables with time. That's what it's all about. We're going to be looking at it in time, unlike the steady state in which everything is fixed. All right, assuming constant conditions as what is written here. The dynamic state actually varies every composition, every component you're going to be having, every variable. You'll be varying it with time to see um, how the process occurs. So now, instead of looking at it, steady state is the usually the ideal state, but the dynamic state now, that's when you're now moving in and then you're now seeing how it is in real life, looking at how the system works and everything. So basically that is it. Now basically most times you tend to use your steady state when you're trying to do the optimization and all that, but your dynamic state you tend to use it when you're trying to control some of the unit operations and then the variables that you're going to be using. All right, so let's look at it, the dynamic state versus the steady state simulation. All right, so the features: time dependency. Steady state is not time dependent, all right, while dynamic state is time dependent. The purpose used for design, optimization, and sizing of equipment, while the dynamic state is for control strategy, safety analysis, startup, and shutdown. Alright, the system conditions. Okay, steady state assumes conditions that are constant and balanced. Like we earlier stated, it's fixed. You understand? The conditions are fixed, they don't vary. While in the dynamic state, you see the fluctuations and disturbance with the transitionings, alright? And then the control system simulation, that's another feature. It's limited or no control system modeling, alright? So basically most times in your steady state you don't really have controls for it exactly. The basic things you can use is logical operations such as the adjust, the balance, and all that. But when it comes to the controls, you don't really use controls in steady states. They are meant for the dynamic states. And then for the dynamic state, you have fully integrated control systems like the PID controllers. All right. The transient behavior, it doesn't capture the transient behavior. Alright, remember I told you that the transient behavior is when it moves from one steady state to another. Now that change is the transient behavior. It doesn't capture that in the steady state, but it is being captured in the dynamic state. Alright, application example. When you are designing your distillation column, you can easily use your steady state to do that. And then when you are trying to do your dynamic simulation, you look more at the startup and the shutdown of that distillation column. All right. Complexity, it's simpler and faster to solve. All right. And then for the dynamic simulation is more complex and computational intensive. All right. So the operator training, when you are training most times, especially in the field, they tend to use more since it's a live plant. They're not working on the steady state. They use the dynamic state for it. So the training they tend to give it's for operators is in the dynamic states, not on the steady state. Right, as I said, it's not suitable and then under the steady state simulation and then excellent for real time operator training. All right. So what are we looking at now? Remember we said that this is the dynamic simulation and control strategies. All right. So now what are the control strategies? Control strategies are systematic methods used to maintain desired process conditions in a plant or system, especially when there are disturbances or change in operation. All right. So basically your controls are used to regulate and maintain your desired conditions. All right. Imagine you have uh, like a particular amount of production flow you're looking at. Imagine you're trying to produce ammonia and then you said your ammonia should be coming out at, you should have a constant production of ammonia, let's say within the range of 1,000 tons per hour. Let's use that as an example. And then if it goes above 1,000 tons per hour, meaning that your system could have issues, or if it's less than that, you know that your system is not optimized enough to give you what you need. All right, so you have to regulate such things, or you have a tank and then you say that your tank should be at 85% full. All right, so anything above 85%, you know that it's too much. And then you have maybe within, shouldn't be less than 50. All right, so basically those are the variable conditions you're looking at. Those are the desired conditions you're looking at. All right, so the idea of the control strategies will help you to maintain your desired conditions. All right, so why are they important? Why are these controllers important? Why are the control strategies important? They ensure safe and stable operations. um yes, they do that a lot, so that in case of temperature, imagine you're trying to, or the pressure of a pipe, imagine your pipe has a capacity that it can take, pressure capacity it can take. Anything above that pressure will lead to rupture of the pipe, so you might not want to exceed that pressure. Likewise, the same thing for the temperature. You have a system that can accommodate a particular amount of temperature, or an operation that shouldn't exceed a particular temperature. So basically you need your controllers to keep this in check. All right, it maintains the product quality. All right, remember in the case of the ammonia, as stated, you're trying to produce a particular amount of ammonia and you don't want it to be excess, neither do you want it to be less. All right, and then you have to keep your operating conditions the same to give you the quality you need. Basically you need that control system for it. All right, it improves efficiency and performance. All right, so it keeps your system in check. It helps the performance to be in check. All right, so responds effectively to changes or disturbances. All right, so when there's a disturbance or change, if you're using like a feed forward controller, it detects the change before it happens and then tries to control the system appropriately, and things like that. All right, so what are the types of control strategies we have? We have different types, but we are going to be looking at just a few of them. All right, so we have the feedback control, and then the description given here, it measures the output and adjusts input to correct deviations, just like your thermostat adjusting room temperature. Your feedback controller tends to work more in things like your AC, and then your iron. Yes, you have a control system like that, a thermostat. It works in that kind of condition. All right. Your feed forward controllers, you have the response to disturbance before they affect the process. All right. So it checks and then notices any form of disturbance before it will affect the process, and then it does what it needs to do on time. Like now, adding cooling water before temperature rises. All right. So imagine you're working with a tank, and then all of a sudden the temperature is beginning to increase. Obviously you need like a control system to cool that, to release water on time so that it doesn't rise to a particular temperature. All right, imagine if we notice in our filling stations there is something that tends to happen, especially when they are dealing with their gas tank. They usually used to have water pouring on the tank um, almost constantly. All right, so most times you can use something like a feed forward controller for such situation. All right, instead of them just wasting the water continuously, not really checking the temperature of the tank, just because some of those filling stations do such a thing. All right, so you can use a feed forward controller in such situation. Now you monitor the temperature of the tank. Once you notice that okay, the temperature is beginning to rise, it hasn't gotten to the um, temperature where it will begin to cause serious expansion of the tank, and which can lead to the explosion. Then you can, once it hasn't gotten to that range, but it's that the temperature rise, you can open the valves, and then this kind of controller can open the valves and allow the water to pour on such tanks to allow it to cool to a particular temperature. And once it has cooled down to a particular temperature, it will switch off those valves, and then the water will stop pouring. So that way you're saving water as well. So those are the kind of things they need in such stations. All right. So you have the cascade control. Now the cascade control uses a secondary loop to improve control of the main process variable. All right, so usually in cascade control, you have two controllers. You have the primary and the secondary. All right, so the primary tends to improve that of the secondary. The secondary tends to improve that of the primary. All right, so the primary tends to have your set points, and then the secondary is still under and controlling every other thing to be in accordance with that set point. All right, so as we go further, we'll see how the cascade controller works. So it's usually used for controlling reactor temperature via jacket flow. All right. So imagine you have, let's say you are using a heat exchanger, and then this particular heat exchanger is supposed to be working within a particular temperature. All right. So, or let's say a heater. Let's say heater. So the heater is supposed to be working at a particular temperature, and then you have to regulate the flow of your inlet. All right, the flow of the inlet. All right, so whatever you are trying to put into it, that's to regulate the flow. So the secondary controller will be regulating the flow according to the primary controller, which is regulating the temperature. All right, so basically that's how that works. We have the ratio control, which maintains a set ratio between two variables. All right, so when you are mixing two components in a fixed proportion. All right, so imagine you have two variables you're trying to regulate at the same time, or you have two components you're trying to feed into a system. let's use, for example, you're trying to do a reaction process, all right, and then you have two reactants. Okay, so now you have to control the flow of these reactants. Maybe you're having 2 to 1 mole ratio, that kind of thing. So basically, what you have to control the variables together at the same time so that one doesn't exceed the other. So that which is of 2 moles, you have to keep it at 2 moles, and then that of 1 mole, you have to keep it at 1 mole. So basically, these two have to be kept. Um, they have to be controlled simultaneously. That's why we have that ratio control, such a thing. Yeah, all right. Then we have the split range control. It's a single controller that operates multiple final control elements in sequence. Alright, the example is one valve opening, closing, another closes. Alright, so basically, if you open a valve, um, let me see. Alright, so basically, if you are having two pumps and then you have one is feeding cold water, the other is feeding the hot water, and then maybe in that particular tank, you have to regulate the water at a particular temperature. Let's say we want to keep it warm at, 30 30 degrees. All right, we want to keep the water warm at 30 degrees, and then remember we have two inlets. We have one that is feeding the cold water, we have the other that is feeding the hot water. All right, so whenever the temperature begins to exceed or go higher than, let's say 35 degrees, basically you switch off the valve supplying the cold water, sorry, supplying the hot water, and then you allow the cold water to be supplied for a while to regulate the temperature to about 30. And then if anything happens and then the temperature begins to go to about 25, and then you need to increase the temperature of that mixture you're having, then you need to increase the you have to shut down the cold water valve and then open the hot water valve so that it will pour the hot water into it and then increase the temperature to the range we are looking at. All right, so basically that's how the split range control works. And then the override control with prioritize safety or constraints by choosing the most crucial variable to control. All right, so example is preventing pressure from exceeding limits. All right, so imagine in the case of the pipe I talked about, where your pipe has a pressure limit. All right, so this override control tends to look for a constraint, a variable to help reduce the pressure. All right, so if it's going to reduce the feed flow, it does that. Or if it's basically, if the pipe is passing something like a liquid and then you're using a pump, all right, so it might reduce, or if it's passing through a valve, it might reduce the opening of the valve. Sorry, yes, it might reduce the opening of the valve or try to shut it down so that the pressure will not be too much. That's of the feed going into the pipe. I hope you understand that. So basically this is what we are looking at, and then from here we'll be going into the simulation environment. So we're looking at three basic control systems: the PID, the feed forward, and then the cascade control. All right, so we're going to be looking at this on Aspen HYSYS to see how they work in the dynamic process. All right, so see you in the next video.